quantum textbook with Qiskit. Um, Definitely recommend learning Python. It's probably a requirement for at this point, just because this is all going to be Python and Python library, Qiskit, which is the quantum computing textbook that I'm using. Um, if you haven't already, pull up your notebook and definitely run this with me, just because it's a lot better to experience things and do things than it is to um, just watch. Just watching won't get you anywhere, but actually running these experiments and following the textbook with me will definitely make you become an expert. And that's my goal, is to become more of an expert in this field and then use it for business purposes to find CRISPR edits in the human genome that can, I don't know, make us live forever, something like that. Who knows? I'm gonna find out. Alright, chapter 1.4, creating an Xor Gate. Now we're going to be encoding an input. Now let's look how encode different binary strings as an input. For this, we'll need to know what is known as a NOT gate. This is a basic operation that we can do in a computer. Simply flips a bit value from 0 to 1 and 1 to 0. For qubits is an operation called X that does the job of the NOT gate. Below, we create a new circuit dedicated to the job encoding and all, and QC encode. Okay, cool. Boom. So this is encoding it, quantum circuit, and then we're going to apply encode.x to the 7th position, so the very last qubit, and then they're going to print out or draw it, which prints out this for us. And this was what we did earlier. If you remember, we were doing your first quantum circuit. Okay, so in 4 we basically added an X gate to the very last qubit, which is cool. You're on your way of learning. That's your very first, gate application, so you're already a quantum programmer. Whoa, whoa. Extracting results can be done using the circuit we have from below. QC underscore output, adding two circuits with using QC underscore encode plus QC underscore output creates a new circuit with everything needed to extract an output as needed at the end. Now we can run the combined circuit and look at the results. And just so that you can see the results a little clearer, the first is a 1% chance of it being, so there's a 100% chance of it being this number, which is 1 0 0 0 0 0 0 0. Cool, cool. Now our computer puts a string instead. The bit we flipped, which comes in qubit 7, lives in the far left of the string. This is because Qiskit numbers the bits in a string are from right to left. Some prefer the number of their bits the other way around, but in Qiskit's system certainly has its advantages. When we are using bits to represent numbers, specifically, it means the qubit 7 is telling us how many 2 to the 7th power we have in our numbers. So by flipping this bit, we've written the number 128 in our simple 8-bit computer. Now we try out writing another number for yourself. Do your age, for example. Just use a search engine to find out what the number looks like in binary. Okay, there you go. It includes 0B, just ignore it, then add some zeros on the left side if you are younger than 64. not sure what they want us to do here. Let's keep looking at other stuff and remembering how to add. I'm just gonna read over this quickly. I don't think an adder. Okay. Oh, so they're gonna basically an adder gate means. Okay. So you can go over this yourself. It's just basically saying that they're gonna add simple. It's basically simple math. Just showing you an adder gate, I guess. Adding with Qiskit. Let's make half our adder using Qiskit. This will be a part that encodes the input, the part that executes the algorithm, and part that extracts the results. The first part will need to be changed whenever we want to use a new input, but the rest will always remain the same. You can see it better with the white, I guess. What system? Okay. Go back to dark. 2 bits we want to add are encoded in qubits 0 and 1. The above examples are encoded in 1. Both of these qubits seek the resolution of 1 plus 1. The results will be strings of 2 bits, which we will read out from qubits 2 and 3. All that remains is to fill an actual program which lives in the blank space in the middle. Okay. The dashed lines in the image distinguish different parts of the circuit, although they can be more interesting to use too. They are made using barrier command. The basic operations of a computing are known as logic gates. We already used the NOT gate. This is not enough to make half our adder gate. We could only use it to manually write out answers. Since we want the computer to do the actual computing for us, we need more powerful gates. What is this doing? Sorry, I don't know what it just did. I was just at this 0.3 and then it. Okay. Oh, it just read it in the way it was supposed to be read. Okay, sorry. It's just like sometimes it jumps in types of whatever it's doing. Okay. So I'm over time, but I'm just gonna finish it real quick. So this will be the last video. It might go over 10 to 15 minutes. I apologize. I'm trying to keep it under 10 minutes, but we'll just go as fast as we can, okay? And if you need to rewatch it, definitely do so. Like and subscribe, and for more of this quantum computing textbook. I'm going to be going over this one, and then I'll probably do Google's Circ next after Qiskit, just because, yeah, it seems like a next step, just because that way you can learn multiple systems. And the Qiskit library is cool, but you know, if Google's Circ library ends up being, you know, better, at this rate, we still don't know which one would be better, just because they're both really early quantum computing software choices, and no one really knows which is better, not just yet. I'm sure there'll be papers out that'll prove one way or the other. So yeah, let's get going. Okay, so we just added, or we're doing half an adder gate, right? And this is a CNot gate right here. That's what it looks like. In quantum computers, the job of an Xor gate is done. Oh, okay. So this goes over some of the different things. Okay, 2 bits, we want our encoded in qubits, 1, 0. Above example encodes 1, both sides, okay. 2 bits, hash lines, it's a barrier, so that's a barrier. I was going over that before it changed into this different output. The rightmost bit in all 4 of these answers is completely determined by whether the 2 bits we are adding are the same or different. So far, 0 plus 0 and 1 plus 1, where 2 bits are equal, the rightmost answer comes out 0 for 0 plus 1 and 1 plus 0. We're adding different bits. Right bits is 1. To get this part of our solution correct, we need something that can figure out whether or not 2 bits are different or not. Traditionally, in the study of digital computation, this is an Xor gate. Okay. In quantum computers, the job of an Xor gate is done by this control NOT gate, or CNot gate. Right here. Okay. Since it's quite lame, we usually just call it CNot. In Qiskit, it's CX, which is even shorter. In circuit diagrams are shown as in the image below. There you go. Switch it real quick. So, those of you that like the white flash thing, let's close that, make it a little bigger. You can read all that next by yourself. I'm just going to be covering more of like visual things just because I like running the program and then actually explaining what the code does. So here the code, we're summoning QC, and that's going to be equal to the quantum circuit, and we're going to make 2 qubits. Oh no, it's written like that. That's kind of weird. Oh. I gotta find out what this comma does in the end of this. But and this in a CNOT gate, the 0 is the first, the controller, and then the second is the qubit that's going to be controlled, and you put those in, and those are the positions. So this is 0, which means the first qubit, and this is 1, which means the second qubit, and this is the CNOT gate right here. And then these are measurements being made on the circuit, and that's an XNOT gate, because without this being a 1, so all states start at 0, right? All qubit states start at 0, and this X gate switches it to a 1, so that this CNOT gate actually does something to the second qubit. There you go. If you execute this circuit, you'll find the output is 1, 1. We can think of this happening because it's either of the following reasons. CNOT gate calculates whether the input's values are different and finds that they are, which means that it wants to output 1. It does this by writing over the state of a qubit 1, which we remember is on the left string bit, turning 0, 1 into 1, 1. The CNOT gate sees that the qubit 0 is in the 1 state, so it applies the NOT qubit to 1. This flips the 0 of the qubit 1 into 1, and so it turns out 0, 1 into 1, 1. Here's a table showing all possible inputs and corresponding outputs of the CNOT gate. 0, 0, output 0, 0, 0, 1, output 1, 1, and then 1, 1 0 1 0, and then 1 1 is 0 1. And it just changed the format in which that was read. Okay. For half our adder, we don't want to override one of our inputs. Instead, we want to write the result on a different pair of qubits. For this, we can use two CNot gates. Okay, and we'll run this. And let's take a look here. So this is the first we want. Oh, I think this is which ones are measured. Because this is the amount of qubits you want. And it looks like the only ones that are being measured are the last two. So I think it probably has something to do with measuring the last two. This part of that code. Right? So it applies the next gate to 0. It applies an X gate to qubit 1 as well. So qubit 0 and qubit 1 get an X gate. And then it's going to do a barrier, so I guess it looks simpler to see. And then they add a CNot gate to qubit 0 to control qubit 2, and then another CNot gate to qubit 1, 2. So this is going to be 0 because we flipped it once and twice, and this is a 1, so it activates this, right? And this is a 1, so it activates this. So overall, we're activating it twice and flipping it from 0, right, to 1, and then 0 again, and then it's being measured. So that's what's happening here, and this is just drawing the circuit out so that you can see it visually. I think that's pretty much all they go over. They do add some more complicated gates here, so if you want to check that out, definitely do so by yourself. Play around with this. The histogram view is pretty nice, and I'll try and go over like the way this is printed out and why it's printed out that way. Mostly it's just a way to keep track of things. And this is a 100% chance of it being qubit 1 0, and it's like it's a weird explanation. Right to left, left to right, something like that. Okay, we'll run this other last thing and see what it does. Oh, that's just telling you what kind of packages it's running right now. So if you need to try and run it locally or something, you can do that. Alright, so that's all I'm going to go over today. I hope you enjoyed the 3 parts video. I'm sorry I couldn't get it all separated to 7-minute videos, but I'll go over everything that I just covered. So this is just atoms of computation. So they were explaining what computation is, what bits are, right? We went over that. In regular computing, this is a regular computing diagram. This is a quantum computing diagram. We built our first quantum circuit. Then we kind of draw it out in measurements. And then this is basically just running a simulator and putting it out as a histogram, which is a chart. So basically you can represent it in chart form and circuit form now, right? So that's what we learned mostly so far, is how to represent quantum circuits in chart mode and histogram mode. And then applied some different quantum gates in different positions. Then we learned to add with Qiskit. There you go. That seems like all we did, and I hope you enjoyed this video. Make sure to like and subscribe, and we'll get learning together. If you can think of any ways I can improve my videos, definitely let me know, and I'll get back to you.